Welcome back to Topics in Statics. This is going to be the first of 5 lectures on vectors. Vectors are tremendously important in physics and engineering, and we're going to try and get a handle on how to deal with them in a practical nature. There's 2 basic ways to think about vectors. I can think about a vector as an arrow pointing in space, or I can think about a vector as an ordered list of numbers. In general, I tend to think of a vector as an arrow pointing somewhere in space. Now, it's a real good mental picture to have of a vector, but it's not real good calculation-wise. And so when I start calculating, I talk about a vector as an ordered list of numbers. This vector is going to deal exclusively with a vector as an arrow pointing in space. So we're going to not worry about the ordered list of numbers yet. So let's start off and talk about the anatomy of the vector. Just get some terminology here. Here's a nice vector drawn on a page. This point down here is what I call the tail of the vector. This point up here is what I call the head of the vector. The length of this thing from here to here is what I call the magnitude. The longer this arrow is, the greater the magnitude of the vector. This vector points along this dashed line, and this dashed line is what I call the line of action. And we'll see why that's important later. And then if I wanted to introduce some kind of coordinate system, I'd have to define a reference axis. So here's the reference axis. And then I could put in an angle here and talk about the direction, the magnitude and the direction. But I have to define some kind of reference axis in order to do that. So here's 3 vectors. So here's the question. Here's a bunch of vectors on this page. Which of these vectors are equal to R? What does it mean when I say that 2 vectors are equal to each other? Well, what it means is that they have the same magnitude and the same direction. So looking at these vectors, I can tell right off the bat, vector B just does not have the same magnitude. It's out of the picture. But all these other vectors have the same magnitude as R. So which of them also point in the same direction? The only one that points in the same direction is E. The vector D points in the opposite direction, but so it's not equal. So one of the first things I can do is I can scale vectors. Right? When I talk about scaling vectors, I scale a vector by multiplying it times a scalar. Right? That's why they're called scalars, because that's what they do. They scale vectors. And what that means is they make them longer or shorter. So if I multiply a scalar times a vector, it changes the length of the vector. So I've got several vectors up there. A couple of things to notice: if the scalar I multiply it by is negative, it flips the vector around and makes it point the opposite direction. This whole process is called scalar multiplication. Do not confuse that later with a scalar product. They're different things. A scalar multiplication means I'm multiplying a vector times a scalar. And all that does is change the length of the vector. So then I can get to vector addition. And this is not particularly a practical method of vector addition. I've got these 2 vectors, A and B. So let's take the vector A. Here's the vector A. And then I'm going to put the vector B over here and put them tip to tail is how I'd refer to that. And then I can put them over here again. I'm going to start at the same place that A started over here. I'm going to do it again in the opposite order. And you see where I've got 2 vectors tail to tail. That's where I'm going to start. And then I've got 2 vectors that are head to head. That's where this resultant vector is. That's the vector R. And so this top triangle is A plus B, which is equal to R. And this bottom triangle is B plus A equals R. So just by drawing this nice little simple picture, I've demonstrated that vector addition is commutative. I can do it in either order. A plus B or B plus A, it's the same thing. This is a nice mental picture to have in your mind. I'm never going to actually add vectors doing this. So just keep this picture in your mind to understand what's going on when you add vectors. So let's talk about the vector addition of forces. Let's say I've got these two forces, F1 and F2, are acting on this stanchion. Well, the combination of the two produces some resultant force on that stanchion, and I can find that resultant force as it shows in the picture on the right. Nothing too astounding there. But what's also interesting is, let's say I've got some force acting on this. It's two struts that are joined together, and there's a force acting on this combination of the two struts. And so I want to know what is the force on each of those two struts. And so I define two directions, u and v. And what I want to do is I want to break up this vector f into what I call the components in the u and v directions. Essentially what I'm doing is I'm going backwards from vector addition. I'm taking a single vector, I'm going to break it up into two equivalent vectors. That when I add these two vectors, fv and fu, I get the original vector f back. And so all I've done is draw that picture. It's the same picture. Now, when I go about doing this, right, I reduce the parallelogram. Let's make it into a triangle. Here's those same vectors, f, fu, and fv, drawn as a triangle. You'll notice it's not a right triangle. Because it's not a right triangle, I can't use trigonometry. Trigonometry deals with right triangles. This is not a right triangle. So what I have to do is use the law of sines and the law of cosines. This is something you learn in geometry. And I've drawn you a picture down here of a triangle. This picture of a triangle, you notice that the capital letters A, B, and C refer to the length of the sides, and the lowercase letters A, B, and C refer to the angles. None of those angles is 90 degrees. So this top equation is the law of cosines. It just says c squared is equal to a squared plus b squared minus 2ab cosine of c. You notice that the length I'm solving for, c squared, the cosine I'm taking is the lowercase c. Capital C is opposite lowercase c. Right? These always go opposite. And then the law of sines just says the ratio, the length of A over the sine of A is equal to B over the sine of B plus C over the sine of C. And so I can break this vector up into components using the law of sines and the law of cosines. Another thing to notice is, let's say that the angle C is 90 degrees. Then what happens to the law of cosines? If C is 90 degrees, then that becomes the Pythagorean theorem, which is a good thing. I like the Pythagorean theorem. So that's about enough with vectors as arrows. Like I said, vectors as arrows, it's a great way to think about vectors, but I don't necessarily calculate a whole lot with vectors as arrows. So next time we'll move into actual calculations, and we'll talk about vectors in 2 dimensions. That's it for now. See you later.